Hello, good afternoon. This afternoon, I'd like to continue with the chapter 2.2, the pavement materials, constructions, and testing of the aggregates. Okay, so this is the part 2 of this chapter. So in this chapter, I'm going to talk about the stabilizations of the pavements and subgrades, and also the rehabilitations of the pavement, and also the testing of aggregates. Okay, so first we start off with the stabilizations of pavement and subgrades. This stabilization is a process whereby additives are used to improve the properties of subgrade and pavement materials. So I think we talked about the pavement materials and subgrade before. So the subgrade is the formation level, the soil that has been prepared to receive the pavement materials, and pavement materials is the sub-base as well as the base course, and on top of the sub-base and the base course will be the surface course, which comprise of the wearing cost and the binder cost. Okay, so we're going to look at the different additives that can be added to the pavement or the subgrades. Okay, commonly used additives include the granular materials. Granular materials. We're going to look at each one of them later on. So this one is just different type of materials add to the aggregates. Okay, so just makes it to have a certain type of the particles size distributions. Portland cement or cementitious materials. So these two is slightly different. Okay, the cement is one of the cementitious material. Other cementitious material like the fly ash. Okay, and next one is lime and bitumen and tar. So you can see that the left, the top left is the lime, and then the cement. They looks the same, but they are quite different in the properties. Okay, the cement need to react with water. Actually, it's a binder. Okay, the bottom left is the form bituminous stabilizations, and on the right hand side just show the machine that used to do the stabilization. Basically, they are the machine that are doing the stabilization are quite similar. Okay, so they are like this machine. They are called the recycler or the reclaimer, or sometimes just called the stabilizer. Also, geotextile may be used in the form of as a form of stabilization as well in special circumstances. Stabilize in a way is to stabilize the pavement. We can, it's a similar to other things as well, other like lime or cement or bituminous. So the geotextile it is used as to strengthen the pavement. Okay, actually to distribute the traffic loading underneath the pavement materials, so it can cover any like weak spot in the pavement materials. So that we even it sort of made the surface the pavement materials on top of the geotextile to be even, so they can every part be the same, will be stretched by the geotextile. Okay, stabilization should be considered when it's more economical to use an additive to improve the readily available pavement materials than to use a higher quality and higher cost material from elsewhere. So actually we need to look at uh, the reason or the rationale whether we need to stabilize the material. Okay, so sometimes we need to, sometimes we don't need to, and then sometimes a lot of the time the reason is because of the economics. Because if we can achieve the same strength of the pavement at by stabilization and with a lower cost, then stabilization could be the way to go forward. Okay, examples of the use of stabilization includes the following. So there are 3 points here. To provide a working platform for construction traffic in otherwise soft or loose condition. So the stabilization can provide a platform, for construction traffic. Otherwise, if you just have the sub base, then or even a subgrade, okay, then if it's it'll be too heavy for the construction traffic. So if you can stabilize it, either you stabilize the subgrade or you stabilize the sub base, then actually you can it is possible for the construction people, to do to deliver materials for the construction traffic, to use for this the temporary, considered as temporary rod. It's not the full rod. It doesn't have the full the sub base or the base cost and the wearing cost on top, but it's just the subgrade or the sub base. So it's sort of provide the working platform. Secondly, to improve the properties of the pavement material so that they can be used in higher layers of pavement, or to reduce the pavement thickness required above them. So a material, certain type of aggregate that we use, it could be of certain strength, but with stabilization, whether you mix it with cement or the foam or the bitumen, then actually it can provide a higher strength. Okay, so the stabilization can upgrade the pavement material to a higher strength. Okay. Thirdly, to reduce the effect of moisture on the subgrade or lower layers in the pavement. So the stabilization can actually sort of make the subgrade less less affected by the moisture. Okay, especially for some, the clay soil. If you stabilize with lime, then actually the lime will provide the volumetric stability. So it will not, so the clay will not shrink, will not swell or shrink, when there's a change in the moisture content. Okay, so it can stabilize it, it can provide that stability. Okay, so this one is just a diagram showing the effect of the stabilization. The top one is as we said earlier, is a geotextile or geosynthetic. On the left hand side, without the geotextile or geosynthetic, it is actually, the loading is it provide a bigger effect, the underneath it. And then whereas on the right hand side, so the geotextile help to distribute the loading, and then it doesn't provide a high stress area underneath the wheel. At the bottom, on the left hand side, you can see that it's a previously it was a gravel rod, and then after you stabilize, I'm not sure we can see very clearly, but it's sort of it is a better condition because the stabilized rod, it could be like increasing the strength. Also the stabilization, it can reduce the dust as well. Okay, so because this one, because it's sort of if it's stabilized with cement, then actually sort of it's sort of it can be a sort of concrete slabs. Okay, the factors that can affect the form of stabilization as follow. Okay, so there are different types: 1, 2, 3, 4, 5. The 5 factors. Okay, so first one is a site condition. The availability of suitable personnel and equipment. Okay, so if you want to do the certain type of stabilization, you want to do cement, of course you need to have the equipment. If you don't have the equipment, you can't do that. And then apart from the equipment, you also need the personnel as well. There must be some skilled personnel be able to run the machine, run the operations. Okay. Secondly, depend on the type of the materials, which is the type of materials, and then this will decide what type of stabilization it can be used. Okay, so we can classify the rod based on the plasticity index, PI. Okay, you can see that there's PI less than 10, and then PI between 10 and 20, and PI greater than 20. And the same for the right hand side, PI less than 6 and PI less than 10, PI more than 10. So but this determined by the two, also the material, different type of materials. One is more than 25% passing the 75 micrometers sieve. On the right hand side is less than 25% passing the 75 micrometers sieve. So what does that mean? So these two, the material that pass that classify under these two criteria, they are slightly different. The material with less than 25% passing the 75 micrometer sieve, less than 25% passing the 75 micrometer sieve are commonly used for base and upper sub-base layer. So less than 25%, that means that this one, on the right hand side, less than 25% passing the 75 sieve. Okay, so the sieve is the stack of the sieve are used for the particle size analysis. There are a number of them, and one of the sieve is 75 micrometer. Okay. The materials with greater than 25% passing the 75 micrometer sieve are considered as subgrade materials. So this one, when the sieve it has more than 25%, receive more than 25%, then it's considered as this category, more than. So this one will be the on the left hand side. It will be the subgrade materials. Okay, so the fines, there are more. The material is for the subgrade. Okay. 3. Climate. Example: the lack of water may preclude cement stabilization. So for cement stabilization, we need water. Okay, water to do the operation, because for cement we only react with water. If there's no water, there's no reaction. so it cannot do any strengthening of the pavement. Fourth, drainage requirement. Okay, so the drainage requirement is sort of it can provide actually the stabilized layer. It can provide separation layer, a waterproof layer, you know, because it's not totally waterproof, but sort of if you stabilize for example, the best cost, actually, you know, if you have the some sort of the wearing cost, the asphalt, which is porous, actually the water can run along the surface of the the best cost, which is been stabilized, okay, because it's sort of waterproof. So, and then the pavement usually they have cross fall, so they can fall from the water can run from the middle of the rod to the edge of the rod, okay, along on top of this the stabilized layer. So it also can the drainage it also can prevent the water coming out from the bottom as well by the capillary rise of water. Okay, economics. This depend on the budget of the authorities. You know, how much money they're willing to spend for the upgrading. You know, if they have more money, probably they will do more stabilization, maybe a slightly better stabilization, probably involving more costs. Okay, if their money is a constraint, maybe they just use the minimal. Okay, to maybe they will use less material, less cement, instead of maybe instead of 8%, they might just use 3%, just to save, just because of the budget constraint. Okay, this diagram just show this figure 2.2 just show the different type of the pavement that's going to be stabilized. The pavement with in situ stabilized pavement layers. So the in situ, that means that this is the existing pavement. So you run the machine, you run the machine on the existing pavement. So you strengthen it, strengthen the pavement. So the in situ the pavement layers. So you could this may be because of the pavement is the wearing cost or the bituminous surfacing is quite old. It's a lot of cracks, you know, a lot of maybe potholes even. They can run the machine and can just stabilize the top part of the pavement. Just maybe the best cost. The pavement might be just you know, the 400 mm thick. Maybe for this in situ stabilized pavement or pavement, maybe they just stabilize the top 300 mm pavement. Okay, and also it can be used for the new pavement as well. The stabilized material in new pavement, they can when they're doing the new pavement, they can one layers of the, let's say, the best cost, they can stabilize it with either with cement or with the with bitumen, the formed bitumen. Okay, and then besides the pavement material, could stabilize the subgrade as well. If subgrade is too a lot of clay, for example, we could stabilize it with the lime. So to strengthen the lime, so that the Cbr, the strength of the subgrade can be improved. Okay, so Cbr may be the subgrade may be quite a weak with subgrade, maybe just Cbr only about 3%. With some stabilization, it could improve it to 5% or 8%. Okay. So this diagram, the preliminary selection of binder additive types. Okay, so we will look at it later on as well, but we just briefly we look through on the left hand corner, the left hand column. We can see that there are different type of binder, the cement and cementitious blends, and then lime, bitumen, and then bitumen can blend with the lime as well, granular, dry and powder, polymer, other proprietary chemical products. Okay, we look at the different type of additives. We can see that they may be suitable and doubtful or not suitable. The red one is not suitable. See the green one, these are light green, then they are suitable. For example, lime is suitable for this more than 25% passing the 75 micrometer sieve. That means it's subgrade. So it's suitable for stabilizing the materials with the PL, plasticity index, more than 10%. Okay, it's quite a plastic material that then we can use the lime to stabilize it. And even for the materials, the pavement materials, this is which is less than 25% passing the 75 micrometer sieve. So when the plasticity index is quite high, more than 10%, the lime can be used as well, because there are quite a lot of plastic material inside there. Okay, so we could use it when the plasticity for some reason is quite high. Okay. And we look at the other thing, for example, the cement usually it can be the cement or cementitious. It can be used for all types of the pavement materials, all type of the plasticity index. Okay, but for the subgrade, it can only be used for the subgrade with low plasticity, less than 10. Okay, bitumen not suitable for the subgrade, but it's suitable mostly for the pavement materials with less plasticity. That means that the plasticity less than 10. So that in this category. And other thing, the granular, mostly for the low plasticity index. Okay, so granular first we look at the granular stabilization. The granular stabilization, it is the improvement of one materials by blending it with one or more granular materials. This type of stabilization provides a direct means of altering the particle size distribution. So we the site, they order some these aggregates from the quarry. There could be just certain mix in the aggregates. Could be, but it may not be to the spec of the for the project. So maybe it's lacking of certain sizes of the materials. So then with the granular stabilizer, we can just mix on site. Okay, so that they have provide the right material. We can improve the stability of the pavement. Okay, so the granular stabilization may involve the following: mixing of materials from various parts of a deposit at the source of supply. So actually it can be done at at the source of supply, like at the quarry. The quarry, they usually have the stockpile of material of the different aggregate size there, so they can mix at the quarry site. Secondly, mixing of selected imported materials with in situ materials. So you could have a selected material, and then you could get it from and imported from somewhere else, maybe from another part of the country. You just can mix it so that to achieve certain particle size distribution. Thirdly, mixing 2 or more selected imported natural gravels. So it could be for certain construction, they even could use the natural gravels. Of course, we prefer the crushed products, crushed aggregates products, for example, the limestone or basalt or granite. But sometimes in certain places where the pavement material is quite expensive, they could use natural gravels, even the sandstone, okay, for the road that are not heavily trafficked. Okay, mixing of recycled materials with existing pavements. So we could mix the existing pavement, we could add with the recycled materials in it. Okay, so whether it's a new or the old, or this a new pavement, and then you probably need, if it's existing pavement, you want to mix it with the recycled materials, probably you need some machine to do the mixing. Okay, usually they have a certain type of machine called the recycler. Okay, where's the machine? They just show. Let me just show you where this machine that they can do the mixing. So this is the material. This is the machine that we can use. This is the recycler. They can, if you have any type of material that is recycled materials, if you want to mix with the existing material, then you need to use a recycler to do the mixing. Okay, the next one is the cementitious stabilization. Okay, so we from the word cementitious, okay, actually, it doesn't just mean cement alone. It actually it means that you can, it's inclusive of cement or supplementary cementitious material. So other materials, fly ash is I think it's a byproduct of you burn the coal in the coal, for example the coal power station to provide the electricity to generate electricity. So there's a byproduct which is called a fly ash, or there's a pulverized granulated blast furnace slag. Okay, so I think this one is, the furnace when you try to manufacture some like steel products, it will leave behind some slag, the granular blast furnace slag. So this one, it can be used as a stabilizing material, as additives. Okay, so in this case, it's under the category of cementitious stabilization. So the primary reaction of the cementitious binder is between the binder and the water in the host material, which lead to the formation of the cementitious material. So you could apply in the pavement, either in the best course or the sub-best, and you could put it in the subgrade as well for the cementitious material. But there must have water for the reaction to happen between the cementitious material and the to have reaction. Okay, for the cementitious material, so they can form the binder for the host material. This reaction occurs almost independently of the nature of the granular material. So the reaction is it is not dependent. It's not the reaction is nothing to do with water and the parent material, the host material. Okay, it's just the reaction is just between water and the cement, or with the fly ash, or these are GGBFS, you know. So for this reason, the cementitious stabilizing binder can be used to stabilize a wide range of material in subgrade and peppermint material. So it can be used for a lot of materials, you know, the line, you know, for this different type, the different plasticity index, you know, we can use different type of material. Most of material you can use, you know, different type of basically the whether it's sedimentary rock, or whether it's sedimentary like limestone, or whether you can use for the igneous aggregates, which like the basalt or granite. You can use any type, even sandstone. I think you can use it as well. Okay, the two important effects of the materials to be stabilized. So for this cementitious stabilization, the two important effects is the reduction in the moisture susceptibility. This one mostly in the I think for the subgrade. You know, for subgrade, you know, if it's the subgrade, it might be, you know, if there's a lot of moisture, the strength will reduce. But when you stabilize it with cementitious material, then the strength will not reduce, you know, even in the presence of heavier moisture content, you know, and secondly, development of interparticle bonds in material to be stabilized. So it can bond the aggregates, the subgrade, for example, the subbase or the base course. If you stabilize with cement, it will bond the aggregate together. So previously it was called unbound, but now with the cement it will bound. So it can become, you know, it's not like a concrete slab, but it can be like a weak concrete slab, you know. It can provide more strength than the previously unbound aggregates. Okay, let's see a short video clip on the cement stabilization. Just go to my cement stabilization. Let me see. Stabilized Okay, the stabilization, it involves the pulverization of the materials to be stabilized, spreading and mixing of the cement stabilizer, mixing it water and with the material, reshaping, compaction, and curing. So it will sometimes it's a one run or two runs. So usually, like for existing pavement, if it's a new pavement, probably just one run. You don't need to, you put aggregates on top. Let's say you're going to stabilize the best cost. You just after you lay this one aggregates, and then you spread the cement, and then you just do a one run with the pulverizer, and then but if it's existing pavement, they need to do the first run is to crack to mix the existing pavement, so to actually to crack the wearing cost, and then the best cost to mix it to whatever depth they want to do the stabilization. It could be like 300 mm thick. So it involves the pulverizing. This is machine pulverizer or stabilizer or reclaimer. So they have this rotary action. This what do we call this crush? It's not crushing. It's the rotary action. This the teeth or the tooth. So it can cut to certain depth, and so the water truck, the hose, the tap, the hose, there will be the hose connect to this this here, and then when the machine is running, they just spray the water inside, so to mix the water with cement and the material for the reaction to happen between cement and water. Okay, so the next one we're going to look at is lime stabilization. Okay, so lime mostly is used for the subgrade. Okay, so actually the process is quite the same, but just that in this case the lime stabilization, they don't push the reclaimer doesn't push water truck in front. Okay, I think I go to just turn this off. I go to the video straight away. Lime stabilization. So the lime truck is going across the rod. This is actually the subgrade. So this stabilizer is the Granular Materials. Subgrade is quite weak. Lime stabilization of the subgrade, soil, and granular beds and subbeds is usually undertaken. So, what are the purposes of the lime stabilization? 1, 2, 3, 4, 5 of them. To increase the bearing capacity, whether it's a subgrade or whether it's even the best, you know, mostly for the best or sub best with the high plasticity, like plasticity index more than 10%. 10. Secondly, to reduce the plasticity and seasonal swell and shrinkage. This particularly is applied to this clay. Clay is because it's a very high plasticity, so it can exhibit those that type of the swell and shrinkage behavior, which is undesirable. So the mixing with lime to stabilize it will reduce this undesired attributes. Reduce the moisture sensitivity. So even so, after the lime stabilization, so the subgrade is less sensitive to swelling or shrinking because of the water. Improve compactability. So with this, because the lime, it will strengthen the soil, the subgrade, subgrade and tools, but it's not as as noticeable as the cement. Cement is stronger for strengthening. Lime is not really. It's not so much for strength, but I mean compared to the cement or to the bitumen. Okay, so but when you strength it will especially if after you stabilize the subgrade with the lime, it will be easier to compact because the soil maybe initially was quite weak, quite soft. After you stabilize with lime, it will be a bit harder and easier to compact. Reduce the in situ moisture content. Usually liquid lime to provide trafficability for construction. So this is a bit like the soil is you can just stabilize it with the lime without constructing the pavement, and then it can be used for the construction traffic. You sometimes because it's sometimes more economical, for the contractor to not to construct the pavement first during the construction. There's some building projects, because they don't want to finish the projects and then you have broken rods and then they have to redo the rod again. So they rather just to have the access rod which is trafficable. Then they only do the rods at the end of the projects. So this lime actually can do that. Lime, if they can strengthen the subgrade, or for certain case they just, if it's the rod is maybe they just put the sub base, then they can do the cement or lime usually a cement stabilization for the sub base. Okay, the advantages of using lime instead of cementitious binder increases with increasing plasticity and fines content of the soil. So if the road projects, you have a high plasticity, then you have to use a lime. If the let's say the soil has low plasticity, probably lime is not the best. Soil with more than 25% passing the 75 micrometer sieve. This one, so the soil, this category, it means for the subgrade, if more than 25% passing the 75 micrometer sieve. So So this one, you know, greater than 25% passing the 75 micrometer sieve, considered as subgrade material. If it's less than this, then it's considered as best or sub-best layer. So generally soil with the PI less than 10, the less plastic soil, then it's better to use the cementitious binder. For materials stabilized with lime, the rate of strength gain is considerably less than the material stabilized with cement or cementitious binder. For strength, the lime will not be as good as the cement or cementitious binder, or even the bitumen binder. Okay, if the aim of the stabilization treatment is to modify the materials to reduce its plasticity, so if you want to reduce the plasticity of the clay materials, that, like for example, then probably you don't need to achieve a high strength, maybe just a bit of strength increase, but not a very big increase. So you could use lower binder content of lime. We don't need to use a lot of the lime. Okay. So unless you really want to have the strength increase, then you probably have to use more lime. Okay. The next one is a bituminous stabilization. It involves adding a suitable bituminous product to granular low cohesion, low plasticity materials. Okay, so the bituminous stabilization, it is also like you can use for the subgrade, which is a low plasticity or for the pavement material, low plasticity. That means that less than the PI less than 10. Okay. So the bituminous stabilization, the objective is to introduce some cohesion into the non-plastic materials, a bit like the cement as well, to make a cohesive material less sensitive to loss of stability with increased moisture. So the cohesive material less sensitive to loss of stability with increased moisture. With increased moisture. So actually the bituminous stabilization could be similar to cementitious material, but one I can think of one situation where we may need to use the bituminous stabilization, because if they don't have that, the place is quite dry, you don't have much water where the water is you can't get it readily. For example, in the in somewhere in the middle of in the central of Australia, where probably not much water, so probably you could use bitumen instead of cement. Various bituminous products, including hot bitumen, cutback bitumen, bitumen emulsion, and foam bitumen, may be used. So you could use different type of bituminous products. Hot bitumen, cutback. We will look at this later on. The cutback means that the bitumen you add with kerosene. Bitumen emulsion is just the bitumen add with is mixed with water. Foam bitumen is a gas, sort of the gaseous bitumen. Okay, just look at the bitumen stabilization, bituminous.
UR 2500 recycles the existing road surface construction by simultaneously granulating and mixing in the foamed bitumen and water. This computer animation shows how the material is processed on the spot. The hot
So the
bitumen
bitumen is being
is formed
pumped in.
16 individual expansion
Then the
chambers
bitumen
of
and the
the spray
water,
bar
because from
and then
bitumen, they have to
injected
pump
into
in
the
both the
mixing
bitumen and the
chamber.
water.
At the same time, water is added to achieve the optimum moisture content of the prepared material mix to ensure perfect compaction density.
So just
UR
one again.
2500
So
recycles
same
the
machine.
existing
So
road
this is a
surface
stabilizer
construction
or the
by
reclaimer pushing
simultaneously
along
granulating and mixing
the
in the
bitumen
foamed
truck
bitumen
as well
and
as
water.
the, I think, pushing along
This
two
computer
truck,
animation
water
shows
truck,
how
water,
the material
water
is
truck
processed
and
on
then
the
the
spot.
bitumen truck.
The hot bitumen is formed in 16 individual expansion chambers of the spray bar
So
and
this
then
cutter will
injected
mix
into the mixing chamber.
bitumen
At the same
and
time, water is added to achieve
material.
the optimum
You see the
moisture
top part is
content of the prepared material mix to ensure perfect
for which
compaction
is wearing
density.
cost, and then part of the best cost. Okay, soil and granular materials normally require the addition of from 2 to 5% of residual bitumen by mass. So probably, you know, for the soil and granular material, you could use for soil as well. I think the bitumen is bitumen. If it for the subgrade, you need to blend with the bitumen need to blend with the some lime for the low plasticity. You know, for the what's that, the pavement materials, they can be applicable for pavement for the materials with PI less than 10, the less plastic materials. Okay, so usually 2 to 5% residual bitumen by mass. Bitumen emulsion content as low as 1% have been used for well-graded materials in dry area. So you could even use like if you 1%, you know, as low as 1% for certain cases. As with other form of stabilization, it is essential there will be thorough and uniform mixing of the stabilizing agent throughout material to be treated. So they need to, you have the reclaimer run through. The reclaimer usually will do the mixing, called the pulverization, or the mixing of the materials. Okay, that's so much about the stabilization of the pavement materials, pavement, or including the subgrade as well. So the next one we're going to look at is the rehabilitation of pavement. So, but this thing, the rehabilitations, actually just to rehabilitation usually is to, is usually apply to the work carried out on an existing pavement. It's not construction of rod. Construction of rod means that it's a new rod, or reconstruction. Reconstruction could be the an existing rod that you need to reconstruct to make new again. But the rehabilitation is it also sort of to bring them is quite a heavy repair. The rehabilitation is more than the normal maintenance, the routine maintenance of patching the potholes. Is more than that. So it's a quite extensive job. But for this rehabilitation, you have to, the width and the alignment of the pavement remain unaltered. The alignment of the rod, we cannot change it. You cannot change the direction of the horizontal alignment. They have to keep the horizontal alignment, and also the the vertical alignment, the slope, and the you cannot cut down the hill. Then that is not rehabilitation. Rehabilitation only, you have to keep the original alignment, and the width, sort of the width, they say that it's, but I think sometimes we do allow to, like, the widening of the rod as well. Sometimes the rod, maybe the old rod is a bit too narrow. I think rehabilitation, we do allow some widening of the rod. Okay, so this rehabilitation work, it could involve the resheeting, overlaying, or some in situ stabilization. Resheeting is for unsealed rod. Unsealed rod, they don't have any the bituminous surfacing. There's no tar seal, or you call it the seal, which is asphalt or chip seal. So it doesn't have that. So it just gravel. So we need to spray a new layer of gravel on top. Overlaying, usually overlaying with it could be the chip seal, or we sometimes call spray seal as well, or it could be a thin layer of asphalt, or even in situ stabilization. We could sort of strengthen the pavement. By bringing in the just previously that we saw the stabilization, to mix it with some cement or bitumen to strengthen the material, strengthen the pavement material. So the resheeting involves placing a new layer of granular pavement on an existing pavement. So this is a gravel rod. Okay, the gravel rod. So that it doesn't have bituminous surfacing. So when the rod is irregular, maybe deformed, or maybe a lot of crack or whatever, the rod, a lot of deformation, a lot of sinking here and there, so they can spread a new layer of these aggregates, and then the roller will come and do the compaction. Overlaying involves the placing a layer of asphalt over existing pavement. Okay, and the additional layer may be of uniform or variable thickness. Okay, so usually it's existing pavement which is old. It is the edge is a lot of cracks, a lot of maybe a lot of holes, a lot of potholes. So they can do the overlay of the this one, the asphalt on top of that. Let's see the short video on that. Overlaying asphalt overlay.
State-of-the-art self-propelled pavers, as well as hand tools to finesse the mix to the desired shape and thickness. The paver generally moves in a straight line as asphalt mix is dumped from the heated truck bed into the paver hopper. The mix is moved to the screed via a series of conveyors and augers. The operator uses his controls to adjust the width of each pass and to direct the flow of asphalt around obstacles. An overlay, at its most basic level, is a series of paver passes, which are 9 to 15 feet wide. The area where two paver passes meet is called a seam or a joint. It is critical that these joints stay as hot as possible so that the mix on each side of the joint can be fused together. Invariably, seams are where the first cracks appear in a new overlay because they are the weakest portion of the overlay. Lute stick skill, as well as crew speed, is the primary defense against premature cracking at the seams. We keep premature seam cracking to a minimum because our crews are so experienced and work so fast. As the paver moves along down each pass, a series of
so there's a lot of roller to roll the finished seal surface. Okay, so we the rehabilitation. So we said that rehabilitation we use the resheeting, overlaying, or in situ stabilization. Okay, the next section we need to look at is the recycling of the pavement materials. It's the reuse of the pavement materials that has reached the end of the useful life in its present environment. You know, the pavement may be old already, there are a lot of cracks on the surface. The bitumen originally was black in color, but when after 10 years or 15 years it become quite gray, so it's quite old. But actually the bitumen, it still can be reused. Even the aggregates, you know, the aggregates, it won't sort of deteriorate. The aggregates, as you know, it will stay for a long time, you know, unless, you know, it will not be crushed by the traffic. So it's because the aggregate is quite hard, quite strong, so it will not be crushed. But only thing is because if when the bitumen is etched, you know, it's all, it become very brittle, and it doesn't have the binding properties anymore. So you need to recycle, rejuvenate it. So it's a reuse of the pavement materials that has reached the end of its useful life, and we can there are few types of recycling involved. So there are surface recycling, in situ pavement recycling, central plant recycling, salvaging and all pavement and reuse it elsewhere. There are four types. So for the surfacing recycling, we have two types. We can so there's a top surface 25 to 50 mm bituminous surfacing. This is mainly to recycle the top part. Okay, so the surface recycling mainly to recycle the asphalt. Okay, you know, if it's the chip seal or spray seal, you can't do recycling because it's too thin. Only about 20. The most is 10 mm or 20 mm. You can't recycle. But for bitumen, for the asphalt, it could be like bitumen could be 100 mm thick. It could be, you know, so they could recycle the top part of it, 25 to 50 mm, the top part of it. Usually the top part that is been that's exposed to the UV light, that's been, the strength has reduced, the property, you know, bitumen has been like oxidized, so it's become very brittle. So they need to only the top like 20 to 25 to 50 mm of the bituminous surfacing that can be recycled. So we could have two methods to do it. One is the heating and planning, and secondly is a heating and scarifying, cold planing or cold milling. Okay, so we look at the heating and planning, the in situ, you know, the surface recycling. So we look at the video on that. Central plant in situ hot in place recycling.
Propane gas heating units utilize convection to transfer heat energy to the bricks in the banks of the heating elements. Using these heating banks, the top 1.5 to 2 inches of the pavement riding surface is heated and softened. The heated and softened top layer of asphalt pavement is then milled and augered into the hot-in-place pavement recycling unit. The remixed and recycled pavement is then laid and compacted at 225 to 230 degrees Fahrenheit. No tack coat is required due to the excellent thermal bond created between the remixed pavement layer and the underlying pavement surface. If the recycled pavement is going to act as the finished riding surface, some public transportation agencies require that a small percentage of virgin asphalt mix be added to the recycled pavement prior to replacement. If a separate riding surface is to be applied, the 1.5 to 2 inches of recycled pavement can be remixed and put down without adding any additional virgin asphalt mix. Small quantities of additional construction materials may also be added to rejuvenate the asphalt binder in the recycled mix. For this job, a small quantity of polymer-modified asphalt emulsion is sprayed from a separate liquid holding tank on the hot-in-place recycling machine onto the re-engineered pavement mix. The recycled loose mix is finally distributed, leveled, and compacted to target pavement density using mechanical rollers working behind the hot-in-place recycling.
Okay, so there is a surface recycling of the pavement, the existing pavement. So they just use the heat, they hit the surface, and then they just scratch it, and then we lay we do the pavement on top. Okay, the second one is the core planing on core milling. To it. Okay, so this is the two types are a bit different. One is the hitting, one is the first one is the just now you saw is you need to hit the surface. The second one, first one you just everything they do on site, in situ, they just they don't need to bring the material to elsewhere they just do it on site. There's something that run one machine over to heat up the existing surface, and then followed by another spreader to spread the bitumen. Lay a new layer on top, and then using the old one as well. Second one is the planning. All the old bitumen is been not the bitumen, or the old asphalt is been planned off. They've been planned off and then put on truck and then bring somewhere else and then rejuvenated. They add some new asphalt, add some bitumen, and then bring in. It's a reuse the aggregates inside. The bitumen is been reused as well, because bitumen you can rejuvenate. You might have to reheat it. You add some more new bitumen on it. Okay. Next one is in situ pavement recycling. Okay, so this is a bit like the cement. It could be like a bit like cement stabilization or the bituminous stabilization. It's done in situ, done on the site. That means this involves the existing pavement. Okay, this method is applicable to existing pavement that has an acceptable standard of horizontal and vertical alignment, but has reached the end of economical life. However, the pavement materials are suitable for rejuvenation by the use of appropriate stabilizing agents. So the process is like below. Okay, just look at the process. You just look at the existing pavement, see which one is good to use. Is it cementitious or whether it's a bitumen? Examine the drainage condition and make any desirable improvement. Remove any pavement and subgrade soft spot. So some place it might be the subgrade which is in question. So probably have to do you have to strengthen the subgrade. You know, if some place is sinking, you know, no point strengthen the top part of the pavement material. You need to repair the subgrade. Okay, so you need to strengthen. You may put some to replace with the suitable material or even with aggregates. Scarify and reshape the existing pavement and add additional materials to any depression. Add the stabilizing agent mix, whether it's cement or bitumen. Probably not very often will be lime. Okay, mostly cement or cementitious or bitumen. If you use cement, then you have to use water. Also even for the bitumen as well, the form bitumen you have to add water as well. Shape, you have to use shape it. Sometimes shape means that you could use the grader to do the shaping and compact with the roller and cure. Where appropriate, apply a bituminous layer. Usually the stabilizing in situ stabilization, you know, after you stabilize it, it actually just form the new sort of base course, the stabilized base course, and then you still need to have another layer of surfacing. You know, it could be a asphalt, or it could be like the spray seal or chip seal. Okay, so we look at the what's that, in situ stabilization.
Recycling with pre-spread cement and foamed bitumen, a Streumaster binding agent spreader pre-spreads small amounts of cement. Computer-controlled metering feeders ensure high spreading accuracy. Behind the spreader, a water and a bitumen tanker truck. The Wirtgen recycler draws in the binding agents via hose connections. The recycler is equipped with push bars to push the two tanker trucks along.
The recycler is pushing
the powerful milling and mixing rotor granulates the damaged pavement layers. The pre-spread cement is mixed in at the same time. A special injection bar with expansion chambers produces the foamed bitumen and sprays it in. Water added to the process causes the bitumen to foam abruptly, expanding it to many times its original volume and distributing it evenly in the mineral aggregate mix. At the same time, the amount of water required for the mixing process is added via a second injection bar. Compaction is effected by Ham single drum compactors, one with a padfoot drum followed by a second one with a smooth drum. Next comes a grader for finish grading. A tandem roller and a pneumatic tired roller complete the compaction process to produce a...
Okay, so this in situ stabilization so actually just now we saw in the short video clip, actually it used two type of binder. Cement, there's, you know, it's in front they got cement truck, they deposit the cement, and then they have got a bitumen as well, bitumen truck in front. So actually they mix the two, you know, for this in situ stabilization, they use two additives, cement as well as the bitumen for the stabilization. Okay. The next one, you're going to look at the central plant recycling. Okay, so it involves removing the pavement from the roadway, crushing or pulverizing it as necessary, and mixing it in the central plant, where controlled amount of new aggregates binder may be added. So this one actually is quite similar to the core planning. You know, the core planning. What is this core planning? You know, they can remove the things somewhere else. They can put a new layer, or could be use a recycled material. You know, for central plant recycling, that means that you have to the materials. I think this one, the central plant recycling, it means that the recycling products, it can be used different for different projects as well. It doesn't mean it has to be from that original position. You know, it can be they have stockpile of some recycling materials on the site, and then they can, when it's necessary, they can use a recycling material from the central plant, and then they can use it as the it can be used as the pavement material, as the aggregates. Okay, the aggregates for the best cost or the sub best, the central plant. Okay, so it involves removing the pavement from the roadway, crushing or pulverizing necessary, and mixing it in the central plant. Okay, so you can do it in this case. I think you actually, it says that you bring the materials from the site here. You need to bring to a central plant. Okay, where controlled amount of new aggregates and binder may be added. Okay, so they recycle at the central. So actually it's quite similar to the core milling, because the core milling, but the core milling is only the I think the difference is that the central plant recycling, it can move a lot of materials rather than just the core milling is just the asphalt, you know, the asphalt only. Whereas for this central plant recycling, it could be more than asphalt. It could be the best cost as well is included. You know, you can bring to the central plant, you know, to be remixed, you know. Central plant recycling. Stockpile it again. So after that, it's placed and compacted in the pavement with the normal equipment and process. Alternatively, after mixing the central plant with or without additional aggregates, the material may be placed and spread on the rod, where it may be stabilized in situ or if desired. Okay, so there's a central plant recycling. So it's a bit similar. I think it involves sort of the core planning as well. You know, you need to bring the thing, the wearing cost, the surface cost. They need to use the machine to mill the asphalt. If you want to move the best cost, then probably you use other machine to move it to the central plant. Salvage. Next one is salvage and the use of reuse of all material. So this one is similar to central plant recycling, except that the material is not brought into a central depot. Okay, in this case, the pavement material on the abandoned section of the road could be salvaged, stockpile, and then reused on the new alignment, either as sub best or best cost. So this this thing, you know, the these are the what's that? This is the all asphalt, you know, all asphalt, you know, they call it reclaimed asphalt pavement. So this thing, they can, maybe the rod is, they no longer in service, so they might, sometimes they want to cross the rod, so they could sort of take away all the asphalt pavement and then stockpile it somewhere, and then later on they can recycle it, crush it, and then use it for another site. Okay, so we have looked through the rehabilitation and the recycling of the pavement materials. So we need to look through the aggregates for the pavement. So I think we have already done more than 1 hour. So hopefully I will try to finish it as soon as possible. So the aggregates for the pavement material. Aggregates for pavement. So we I think the main thing is that we're going to look through some of the tests for the aggregates. You know, the test for the mostly for the I think for the grading, to test for the cleanliness, and then for strength. Okay, so I think we're looking at the 3 only. So the aggregates that are being used, they are from different sources. So the crush and screen quarry products. So this one is, they are the aggregates from the quarry, you know, the from the quarry, you know, that, so they need to they got a lot of big chunk of this one, the rock on site, so they need to use a dynamite to blow it up, and then the big chunk of rock they bring to the crusher, and then to crush it, and then with the successive crushing, you know, you produce a different sizes of aggregates. Okay. Secondly, it's a natural occurring sands or gravel. So these aggregates, we don't use much sand for the rodding, but sometimes we do use we call the quarry dust. Okay, so it a bit like sand, but just the powder form of the aggregates. You know, there's a very but natural occurring like gravel, sandstone. Sandstone is a natural type of the gravels or aggregates. Manufacture aggregates, blast furnace slag. Okay, some this one is for example, the byproducts of this the smelting of the iron. If you want to produce steel, so they got this blast furnace, the slag. So this is a byproduct. It could be used on the pavement materials. Okay, recycle material. So the RAP, so reclaimed asphalt pavement. So we could use you know, just now we saw that one. So this one could be a source of material as well. You know, also other thing, we could use RCC, recycle recycle, what's that, the concrete, you know, concrete, crushed concretes. So the concretes, you know, from the building site, they bring that, they can been crushed, and they can be used for the as a pavement material as well. Aggregate properties. The two categories of aggregate properties. First, number one is the properties dependent on type of the material, on the source of material. So on site, you know, from that quarry, you have certain type of material, certain properties of the material. You know, if some site may be a limestone, another site is a granite, and another site is maybe metamorphic rock. Okay, so they have different, depend on the different site, they have different quality of the rock or the aggregates. Secondly, properties controlled by processing. How you process the aggregates, they can produce certain type of the qualities, certain type of properties. For example, the cleanliness, how clean is the thing, and then the grading of the aggregates. Okay, so we look through the two type of the two categories. Properties dependent on source. So the that will be the toughness of the aggregate. So the strength, hardness, resistant to wear, soundness. Measure the rock, the aggregate is still sound, it's not weathered badly. Density, how is it light or is heavy? Porosity, is it can the water flow through? Is it porous? It means the water can flow through. Resistant to pollution. Okay, it's very tough. Whether some aggregates very tough, so it's very resistant to pollution. Affinity for bitumen. Okay, so how easily the aggregates can be coated with the bitumen. Okay. Secondly, properties controlled by processing, the shape. Okay, then how you the crushing can produce different type of shapes. The particle size distributions. How you going, but the stockpile of aggregates, they have certain particle size distribution. And it may not be the same as the one specified by the projects, the specification, the spec of the project. So may need to remix the aggregates to produce the required to meet the requirement of the project. They need certain this size distribution, so it need to be remixed to produce that size distribution. Thirdly is the cleanliness of the aggregates, silt, clay, organic matter. Okay, so these charts here, these two pages are the same from the same chart. These two. So the flow charts for best cost aggregates test from the New Zealand, the Transit New Zealand, the M4. Okay, this is from M4, from the quarry, the source. So you go to the crushing, the test. These are the test type of test. Test the crushing resistance, test the weathering quality, testing the Cbr for the strength, and after that is a production. You got the aggregates, and you test the sand equivalent. This basically just test the amount of the clay or whatever clay content, and then you check for the clay index or the plasticity index. With the plasticity index, we also talk about it at for the stabilization. If there's even in the pavement material, the plasticity, there are quite varying plasticity in the pavement materials. So yeah, so and beside the cleanliness, we need to check for the broken face content, the particle size, the test the particle size distribution, how the mixing, how the different grading of the aggregates. Okay, but we're not going to look through all the tests. I think we only look at we're going to look at the Cbr. We're going to look at the sand equivalent, the clay index, clay index, plasticity index, and then the particle size distribution. Okay, so this is in the Transit New Zealand TNZ M4. So they specify certain type of tests. For the the different the tests here, or the test name, weathering quality index, crushing resistance, California bearing ratio, all those, the sand equivalent, the crack index, the plasticity index, wet shaving. So they have this certain criteria. For example, sand equivalent not less than 40, crack index not greater than 3, plasticity index not greater than 5. Okay, this one just from certain source, because I think in the TNZ M4 they got a different type of I think for different source they compare to the TNZ M4. Okay, so this one, the for the different type of aggregates, you know, the this one, the Sieve, you know, the for AP40 and AP20, these are the required sizes at the different sieves. You know, the on the test sieve a picture, that means that all these are, you know, they got stacks of the sieves, and then they need to have this cumulative amount of the content on it, which we look later on. Okay, particle size distribution. Commonly used for the granular materials, and the sieve generally use range in size from 37.5 mm to 75 mm. Sorry, 37.5 to the sieve mainly is from 37.5 mm to 75 micrometer. Look at that. This one is the aperture, the size, you know, is 37.5, you know, down to 75 micrometer. It's quite tiny. The hole is quite tiny. So this one will be the, I think, the category of clay. Below that will be the clay. So this one will be the 7.5. This one above 7.5 is the coarse materials, and 7.5, 4.75 and below they are considered as fine aggregates. Okay, yeah, this fine aggregates from 7.5 mm and below, and from above 4.75 they are considered as coarse aggregates. Okay, so they have this stack of this one, the sieves. So they stack up, and then they can, you know, these are sieves from the one on top, which have bigger apertures, and then with decreasing aperture sizes down to the bottom. Okay, the total mass of all material passing each sieve is then expressed as a percentage of total mass of the sample. The particle size distribution is sometimes given in terms of the cumulative percentage retained on the sieve. Okay, so how much retained on the top, you know, on each sieve, divide by the total mass of the sample. Maybe you use like 1 kg, let's say 1 kilogram, 1 kg. So whatever amount you retain on certain sieve, so that one maybe you retain 20 gram. Sorry, let's say 100 gram. So that is about 10%. 100 divided by 1000 grams, you know, it's 10%. Okay, and so on. So the particle size distribution of the aggregate shall conform with the envelope limits defined in table 2 and 3 below when the aggregate is tested. So for the project, usually, you know, the particle size, the distribution, they need to conform to this two table. Okay, table this in the TNZ M4. The table 2 is for individual sample. Okay, so for AP40 or AP20, they need to be in this range. You know, for 19 mm sieve, the percentage needed to be about, you know, the 66 to 81%. You know, 9.5 mm need to be 43 to 57%. Okay. and that on the right hand side is for the AP20. And for the shape control, so shape control, this one is from the Sieve 19 mm. So they have a range of the how much is from 4.75 to 19 mm. It must have this amount and so on, you know. So this particle size requirement, okay, for the percentage requirement for this range of sizes. Okay, so we look at the particle size distribution. I think a lot of you will know it quite well about the particle size, the Sieve analysis in the Geotech. I think it's in Geotech 1.
Ranging from the 1 inch to the number 200 sieve. And in the description of the sieves, when we talk about numbering, the number 200 will mean that there's 200 of these openings in a linear inch. We have the stack of sieves ready to go, and the procedure now is to carefully inspect each one of these sieves for damage. There could be a tear on the material, there could be material stuck on it from previous use, so you want to make sure that you start with proper sieves, and at that point you're ready to pass through the material through the series of sieves. The sieves have been arranged in an order from largest opening to smallest opening, and at the bottom there's a solid lid or a pan at the bottom that will collect the material passing through all of them. We put a lid on it and we're ready for the next step, which is to put it in a shaker. This is set up for 5 minutes so that when we press the start, we start shaking the material continuously for 5 minutes. Once the shaking process is completed, we retrieve the series of sieves from here, from the shaker, and we bring it back to our weighing station. So at this point, we're going to dismantle the setup, and individually, sieve by sieve, we're going to weigh how much material was retained individually in the sieves. So the first thing is to tear the scale, so we start with a 0. And
okay, so there's a particle size distribution. So we need to go run the sieve analysis on the site. You know, usually on the site they have the soil lab. They will need usually is checking for the aggregates that been sent from the quarry to the site. So they need to do the testing and then make sure that, you know, if not according to the spec, they need to remix it to so that they need to, it's just for checking. Actually, that the contractor, they will specify the particle size distribution required for the project, and then ask the people at the quarry to mix it ready, and then they to bring to the site. But they need to check on the site as well, see whether the distribution is the particle size distribution, is it follow the spec or not. Okay, the sand equivalent test. Okay, so this This a few of these sand equivalent tests, and then the clay index test, and the plasticity index. They are all checking about the plasticity of the pavement material, of the aggregates, because you cannot get 100% clean aggregates. They have to wash it, but they cannot get it. There'll be some sort of contaminants, the clay in the aggregate, so they need to test it, make sure that it's not too much of this the clay materials. So the sand equivalent test provides an empirical measures of the quality and quantity of fines in an aggregate. So they actually not necessarily we say the clay, we just call it fines. Okay, the fines, it could be silt or could be clay. So a sample of the fraction that passes 4.75 sieves is placed in a transparent. So this 4.75 actually is like fine aggregates. The fine aggregates, like sand is considered fine aggregates. So we need to make sure that there's not. I think the sand is alright, but we don't want too much clay. Because clay is considered as contaminants. Which is it is undesirable for the pavement. So we don't want to have too much clay materials. Okay, so we are going to check this placed in a transparent graduated cylinder, and then we measure the I think the amount of sand and amount of clay. The sample and solution are shaken in a standardized manner. Solution is in place. So we look through that. I think this is the container. There'll be you can see the sand height. This is I think the aggregate. This thing. If you pass through the 4.75 mm, that means that there'll be quite the particles. Is a fine aggregates. Is all the big one will be excluded already. The big aggregates. So only have this is a very small. Is the fine aggregates 4.75. So after passing that, is you mix with water and some chemical, and then the top there'll be a mixture of clay on top and sand below. We can see how much clay it is. Later on we can see the sand equivalent, the SE, the HA, the clay column HC, and then the fine aggregates column HA. So we don't want, this one, the clay. This one, the clay, if the clay amount is a lot, then this thing will be quite small. So if this one HC is small, then we have a big value. So the less clay that is present, the higher will be the sand equivalent value. So that means that if for clean aggregates, we have a bigger value. We want a bigger value of the sand equivalent. So for example, this one, the sand equivalent, we not less than 40. We want to have a bigger the better. You can have 100 or it's better. Okay, we just briefly look at the sand equivalent test.
Add the material from one of the tins into the cylinder. Take care not to lose any material.
Fine aggregates which pass through the 4.75 millimeter sieve.
Sharply strike the bottom of the cylinder with the palm of your hand to remove any air bubbles that may be trapped in the bottom of the cylinder and shake loose the material from the bottom. Place the cylinder into the mechanical shaker for 45 plus or minus 1. After the 45-second shake period, remove the cylinder from the shaker and then remove the stopper, being careful not to lose any material. Any material that may be sticking to the sides of the cylinder walls. When flushing the sample, push the irrigation tube down to the bottom of the sample in a twisting, turning motion while filling. This flushing and twisting will wash the fines from the bottom of the sample and bring them into suspension. Continue this procedure until you are close to the 15-inch mark. When nearing the 15-inch mark, be prepared to pull out the irrigation tube at the same time the cylinder fills to the 15-inch mark. Let the sample sit undisturbed for 20 minutes plus or minus 15 seconds to allow sedimentation to occur. At the end of the 20-minute sitting period, check the sample and determine the clay reading. If the reading is in between two marks, record to the next higher number. Next, take the weighted foot assembly and carefully lower it into the cylinder. Take the sand reading. Again, if the reading is in between two marks, round up to the next higher number and then subtract 10. 10 is the distance between the bottom of the weighted foot and the reading indicator. Repeat the process on the second sample. When completing the sand equivalent test calculations, round the results of each test to the next higher whole number.
Okay, so that is the sand equivalent test. Okay, so we have no time to we don't have experiment to show this sand equivalent test, so we just show it on the video. The next one is the Cray index test. You know, we look from this the TNZ for this one TNZ M4. You know, when they test for the clay content, you know, either is we test the clay index or the plasticity index, but this here we just look at both of them. So this is clay index test is used to estimate the percentage of expensive clay in natural fines or rock powder. Okay, so the sample of the fines placed in a flask, suspended in still water, hydrogen peroxide. Okay, and then the suspension is titrated using we use a methylene blue solution until the solution reaches the end point. The clay index is a measure of volume of methylene blue solution absorbed by the 1 gram of material. So with the material that we use is they need to pass through this sieve, you know, 75 micrometer sieve, and then you should not get more than 3. So 75 micrometer is a very small, you know, it's down at the bottom. It's I think below this 75, actually this a clay. It's a clay. Above 75 they are considered fine aggregates, but below 75 is a clay. It's a clay materials. So you know we have this the clay. They put the things on the solution and on the piece of paper here. So we just look through the clay index experiment. Where is that? Full depth core milling center plant. Okay, I might have missed out this one. Okay, I think I probably missed out this the video on this one. So I think you just have time you look through the YouTube on the clay index test on this for this. Okay. Plasticity index. This basically just to do the two experiment. The plasticity index. You just do the liquid limit test, the liquid limit test of the, and then the plastic limit experiment. You know, for example, this one you roll the clay into a roll until it cracks, something like that. And then this one you just I think this one the liquid limit apparatus. So you just check the two that they give you two reading, and then the plasticity index is just the difference between the two liquid limit. Again, PL equal to PI equal to LL minus PL. So actually, I think this one, you do these two, the liquid limit is just the moisture content. It's the moisture content of the clay material. So you do it after you do done experiment. I think you put into you check the moisture content of the sample, and the same for this one, the moisture content of the sample, and then the plasticity index is just the PI equal to LL minus PL. Okay, so the plasticity index is a commonly used test to assess the quality of the granular material fines. Its value is a numerical difference between the liquid limit and the plastic limit. It's a range of moisture at which the material behaves as a plastic state, and it's neither a solid or a liquid. So what's the range of the, so you can determine at what range of the moisture content this clay material, it can behave. It's neither is a liquid or solid. It's a semi-solid. Okay, so the plasticity index is quite important as well. You know, I think previously we look at the when you do the stabilization, we need to know what are the plasticity index. You know, if it is, and then it's actually for the plasticity index is used to choose the type of binder that we can use for stabilization as well. You know, whether we should choose cement or whether we should choose bituminous, or whether we choose the lime. So beside testing for the the clay content, the amount of clay, it's also used for maybe for if you want to use to select the type of stabilizing binder to use. So the plasticity index should not be greater than 5 in your test. You know, if the aggregates has exhibit the plasticity index of like more than 5, 10, probably we should reject the aggregates. Same thing for the clay index. You know, if it's greater than 3, probably should not be accepted. So it's sort of like it's checking on the clay amount of clay inside aggregate. So if it's too much, then it should be rejected. If you get something like 3, 4, maybe it's okay. Okay. So lastly, I think we're going to look at the California bearing ratio. I think this one is actually is to check the strength of the aggregates. Okay, the strength of the aggregates that we're going to use. not only for aggregates but also for subgrade as well. Because we measure the strength of the subgrade, we said that what's the Cbr value. So there's the strength of the subgrade and also the strength of the pavement materials after compaction. Okay, usually we measure them after compaction. So the California bearing ratio test was originally devised to provide a method of comparing natural granular materials and crushed rock aggregate beds, and subsequently developed as a means of assessing the subgrade for pavement design purpose. So actually, even later on, when we design for the pavement, we need to know the Cbr of the subgrade. How do we decide the Cbr? I think is on site as well. You look at the natural material. The engineer will be able to assess how much Cbr can be achieved. Maybe 5%, 5 or 6, 7 or 8. Okay, so if the soil is so weak, it's a very weak subgrade, they could stabilize it to achieve a higher Cbr. Okay, Cbr is an empirical value and does not accurately related to any of the fundamental engineering property. Since the material in the test is predominantly subject to shear deformation, the test can be regarded as an indirect measure of the shear strength. So it just measure the strength of the aggregate. The test is normally carried out on material passing the 19 mm sieve. So we choose the material passing through this 19 mm sieve. The 19 mm sieve. So after the material passing through this sieve, and then we use that as a sample for check-in. Okay, the repeatability of Cbr result on medium to coarse grain soil is not as good as fine grain soil. Okay, pavement material must satisfy certain minimum Cbr requirements depending upon the use to which they are to put in the field. So for the subgrade, usually we need to have a subgrade Cbr of 3, and possibly we can do it, compare it to about I think 10. But for the pavement material for subbase, we need at least like 20 or even 40, for the subgrade. And for the best cost, you need to be much bigger, much above 40, 80 or 60, for the best cost. So because from that, the amount of Cbr we can achieve for the subgrade, for subbase and the subgrade, then we can determine the thickness of the basement. Sorry, the thickness of the pavement. So the procedure for the SOX Cbr test. I think I got quite a few videos, but I think I've forgotten to I think I don't have the crash test and then the Cbr, so probably you have to look at the video here regarding the Cbr test. I think probably you have, if you've done the Geotech one, probably have done the Cbr test as well. So for the Cbr test, the specimen is soaked and the expansion is measured. Then the load is applied to the cylinder plunger of 50 mm diameter, and penetration is measured. So you apply the loading on the on this sample, okay, and the penetration should be, how much you penetrate the sample is, it has to be around 1.25 mm per minute. So I think they've got a handle to try to roll it, the things will go down. So then the rate must be like 1.25 mm per minute, and the lots are recorded for they record a range of loading. So we need to record for later on we put the graph, and then we need to find what is the 2.5 mm and 2.5 and 5 mm. We need to see the corresponding loading for these two what's that, the this one, the deformations. Lot is expressed as a percentage of the standard lot. Okay, so it's known as standard lot and respective deformation level, and it's not Cbr because I think there's a crush rock. The standard one is compared to 100% Cbr value, the crush rock 70%. So whatever the sample here, you compare to this 100% Cbr value, and then we can find out what is the Cbr value. So Cbr is equal to X divided by Y. X is the material resistance for the unit lots on the piston for 2.5 or 5 mm penetration. Y is the unit lot for well-graded crush storm. For this one is for 100%, you know. If it's a 2.5 mm penetration, the 100% loading should have a 13.2 Newton, and for 5 mm penetration, it should have a loading of 20 kilonewton. If it's for this sample is for 100, you know, we can look at that. This is a standard loading, you know. This is the loading of the sample at 2.5 mm and 5 mm, and then there's the standard lots for 100% Cbr. So this 3.35 compared to 13.2 and 4.9 compared to 20, you know. So Cbr value usually calculate for penetration of 2.5 meter, 2.5 mm and 5 mm. Generally the Cbr value at 2.5 mm will be greater than that at the 5 mm. In such a case, the formula should be taken as Cbr for design purpose. If Cbr for 5 mm exceeds that for 2.5 mm, the test should be repeated. If identical results follow, the corresponding Cbr to 5 mm penetration should be taken for design. So you see that whether you use 2.5% or 5%, you know, sorry, 2.5 mm or 5 mm, it produces something like Cbr, you know, slightly different. If your 5 mm get a bigger value, then if you repeat it again and then get a bigger value, so you keep the 5 mm. For example, this one, you know, 5 mm, it has a bigger value than the 2.5 mm. So you have to repeat it again. If it's still the same, then the bigger Cbr will be taken. So so the test typical the Cbr test result. This one is no correction necessary. If the line, you know, is go up, is the bottom portion of the graph is a straight line, then we don't need to do any correction. We just take the reading like at 2.5 mm and then at 5 mm, then we get the corresponding like 3.35 and 4.9. So you get the Cbr is you know, the 25.4 for 2.5 mm and 24.5 for 5 mm Cbr. But if the graph, it is the bottom part is you know, it's not a straight line, we need to do some correction. That is corrected. You need to the straight line, the middle, the straight portion part, you need to extrapolate it to cut the horizontal axis, and there's that is the, you know, this point here. So then from this the straight line, the extrapolated straight line, then from this point here we measure off 2.5, and then we draw a line vertically and then go to the left, and then this one will be the 3.15, this one will be the loading 2.15 for 2.5 mm, you know, because this from the extrapolated origin. And then the next one 5 mm just the one the curve 5.8. Okay, so this one is the first one is without correction, second one is with correction. So this one just as exercise on doing the CBR. Okay, so I think that's all for this pavement materials construction and test. So this afternoon we cover the part 2 of the pavement materials construction and materials. So we finished this the chapter 2.1. Okay, so thank you very much. It got, maybe next time we got exam we have time, we can look through this how to calculate the CBR, this exercise as well if you in the class time. Okay, so that's all for this at the moment for the part 2. Thank you very much. Bye.